let's talk about how to make a solar system. Based on what we discussed so far, any successful model of solar system formation has to take into account three things: size and composition of the planets. Remember, the inner planets are all rocky, the outer planets are all gaseous. Direction and orientation of planetary orbits. If you recall, all of the planets orbit the sun in the same direction. And then number three is the size of the terrestrial planets versus the Jovian planets, right? Or the size of the orbits of the terrestrial planets versus the size of the orbits of the Jovian planets. So these three things all have to be explained by any model that we put together for this is how the solar system forms. Well, when we look out in the solar system, we see mostly hydrogen and helium, right? 71% hydrogen, 27% helium, 2% other stuff. All right, that's one thing we have in terms of what is the solar system made of, right? And the answer is hydrogen and helium. And we're in that little 2% of other stuff. Well, if you look out in the universe, we find that most of the universe is hydrogen and helium and a little bit of other stuff. So the solar system is made out of the same thing that the rest of the universe is made out of. So the abundance of hydrogen and helium that comes from the early ages of the universe when the Big Bang created this hot plasma of particles, and that hot plasma condensed into mostly hydrogen and helium, a little bit of lithium here and there, but not much. All right, so nothing else on the periodic table had been created yet. So the universe was just helium, hydrogen, helium, and lithium. As the universe cooled, helium clouds were able to collapse and create stars. And because of nuclear fusion in those stars, the heavier elements began to be created. And then those stars would explode. And when those stars exploded, those heavier elements would be spread throughout their area, their local area, or their galaxy. Right? So we have small or light gases coming together to form stars through fusion causing those creating heavier elements, and then at the end of their life when those stars explode they spread those heavier elements out into the rest of the universe. And if you look at the 10 most abundant elements, 10 most abundant, well, we've got our great candidates of helium and hydrogen, right? And this is just their atomic number, and this is relative abundance in our part of the galaxy, right? Oh, here we go. And this scale, you notice, is a log scale. So helium here to hydrogen to there, that's a factor of 10, right? So hydrogen is 10 times more abundant than helium. And don't let it fool you, iron down here, well, this is a factor of 10 to the fifth, or say basically hydrogen is 10,000 times more abundant than iron. So don't let the log scale make you think that, oh, wait, back here he says it's all helium and hydrogen, and up here suddenly there are all these other elements and they look like they're just as abundant as helium and hydrogen. No, that's not what this graph says. You have to pay attention to this log scale on the side here. This is a factor of 10, 100, 1,000, 10,000, 10,000, 100,000, right? So, and 10 to the fifth is 100,000. So hydrogen is 100,000 times more abundant than iron out here. So if you look at the abundance of all these different elements in our part of the galaxy and near us, this is what it looks like. The current theory on how the solar system formed is that it began as one of these big clouds of gas that we actually can still see out there with telescopes. You can see large clouds of gas out there in our galaxy. So our solar system started for one of these. All right, the whole thing began as a big gas cloud. That gas cloud is going to very slowly shrink because of gravity. You got to remember, you have to remember, even though it's a big cloud of gas, it still has still has mass. In fact, it still has all the mass that's in our solar system. All the mass in our solar system was in this initial cloud. And all of it then attracted each other, just like our sun keeps us orbiting around the sun because of gravity, right? All of it then attracted each other, so it began collapsing. As it collapsed, conservation of angular momentum means it starts to spin faster. So if there's any tiny rotation in this cloud of gas, as it collapses, it's going to start spinning faster, just like a dancer spins faster when they pull their arms in versus having them out like this, right? Angular momentum is going to cause that collapse, is going to cause that spin to speed up. As a result of the contraction and rotation, things pretty much end up in a flat rotating disk, right? Most of the material ends up in this flat rotating disk, with the matter becoming concentrated at the center, most of it becoming concentrated at the center, where we get a little proto-sun. Right? It begins to get hot. It begins to give off energy as the gases collapse down into it. As the gases collapse, they gain speed, right? Thermal energy becomes part of it. The disk heats up. The material at the center fell farthest, so the material at the center is the hottest, right? The stuff out here, still pretty cool. Stuff in here, much hotter. This proto-sun eventually gains enough mass to turn into the sun and become an actual star. The disk around it, protoplanetary disk, is where all the planets are going to form. So at this point, you should know the answer to this. Why do all planets orbit in the same direction in roughly the same plane? Is it because it's just coincidence? That just happenstance, just luck of the draw? If you look at other solar systems, will it be different? Or B, or no, we're going to jump to C. The sun captured them from other stars in a similar process, causing similar motion. Well, other stars passing by would have to pass by exactly the same way every time, right? So no, it's B. They're all formed in the rotating protoplanetary disk. So this is where the planets are coming from, right? Here's the sun forming in the middle. The planets are coming from this disk, right? So things we have to be able to explain. The inner planets are small and rocky. The outer planets are large and gaseous. We've got to be able to explain that. Right? And nebular theory, this theory that we have right now, that the nebulous collapse down into this spinning, rotating disk, can explain that. It does explain that. All right? It's hot. Right? It's hotter towards the center. And if you look at temperature as a function of distance in the solar nebula, you get, oh wow, okay. Here we have liquid water, right? Out here we have all ice. Out here, methane condenses to ice, right? So different materials, pardon me, different materials, different gases are either liquid, solid, or gas, depending on how close they are, right? Rock and metal condense at high temperatures. Ice condenses at low temperatures. And that's why there's this composition difference, right? Ice can't form together to form any sort of body down in here. Why? There's no ice. There can't be ice. It's just too warm for there to be ice. And so the composition is in part driven by the differences in temperature. We have this frost line, it's called, right? The frost line. Beyond the frost line, hydrogen, compounds, rocks, and metals condense. Inside the frost line, rocks and metals condense. Hydrogen and other compounds stay gaseous. Right? So we can't have this big collection of helium gas around the planet Earth because it's just too hot. Right? It's just too hot. If we look out and we look at things like asteroids, all right, so things are going to start by little bitty things, little bitty groups of stuff will join together through electrostatic and molecular forces, and then as once they've done that, things will start getting together because of gravity, right? Materials slowly kind of accrete together. And if we look at asteroids, you can actually see where, yeah, asteroids are made up of little bitty bits of stuff that all slowly came together over a long period of time. Larger objects slam in each other, and that causes them to slowly build into bigger and bigger things. And so if you look at our planetary disk early on, it's going to look a lot like the rings of Saturn, right? It's as they're little small things trying to trying to come together to form a planet. Well, eventually those kind of run into each other and you end up with larger objects until you finally get to, okay, these are the planets and they have actually done a good job. One of the things that planets do, one of the things that makes them a planet, is they kind of clear everything else out around them. So it's just the planet in its orbit and no other junk. All right? And the moons around Jupiter and the moons around Saturn form through a similar process. As the gas and everything that is Jupiter begins to collapse down to form Jupiter, bits and pieces of it that are far enough away clump together to form its moons. And the same with Saturn. Which of the following can condense in the outer solar system? Metal and rock, water and methane, hydrogen and helium. What do you think the answer is here? Which of the following can condense in the outer solar system? Well, late in the game, right? In the outer solar system, you begin sweeping up and grabbing gases out of the planetary nebula, right? You've got early growth, sticking and coagulating, midlife growth, gravitational attraction, late life growth, sweeping out gases. So, terrestrial planets, rocky material that can condense, right? Here was our protosun. Here it's too hot for gas stuff. We get our rocky planets here. Out here, past the frost line, we get our ices, which are abundant enough to be able to grow large enough. All right, and then we begin to capture hydrogen and helium as these get big enough. All right, the frost line is important. Inside of it, all the planets are rocky. Outside of it, the ices can condense and you get begin to gather in hydrogen and helium and build the gas giants. All right, this is illustrating the same thing. Water ice only in the outer parts of the disk. No water ice in the middle. Iron silicate dust particles throughout the disk. Iron silicate dust, planetesimals, ice-rich planetesimals, right? So inside, the only thing gathering together are iron and silicate dust. Out here, you have iron, silicate dust, and ice gathering together. And gradually, as this slowly pulls more and more material together, you get your outer planets, which have swept out all the gases in that area, and you get your inner planets, which have done something similar. Just one last summary. You start with a nebula. You get a planetary disk. At the middle of that is a proto-sun. Eventually that fires up, becomes a true sun, a true star. The inside the frost line, rocky material begins to accrete and form planets. Outside the frost line, rocky material and icy material begins to accrete and form gas giants. As this process continues and these planets form more and more and more through collisions and gathering up material, you eventually end up with the somewhat clean solar system we have today, the Kuiper belt outside of that, and um, that is it for this segment on the formation of our solar system. The next one will be on exoplanets, planets around other stars.